Good afternoon and welcome to the System Design and Management webinar series. The System Design and Management program is a mid-career master's degree program that is jointly offered by MIT's School of Engineering and the MIT Sloan School of Management. The System Design and Management program provides a systems thinking perspective that integrates management, technology, and social sciences to address rapidly accelerating complexity and change in today's global markets. Graduates earn a Master of Science degree in Engineering and Management. The SDM program also offers a one-year certificate in Systems and Product Development. We are pleased to have Mr. Jorge Moreno and Mr. Donnie Hollerschutz present today on renewable energy integration opportunities in Chile. Jorge Moreno is an INODU co-founder with extensive experience in the energy industry in the United States and Latin America. As an SDM graduate, he holds an MS in Engineering and Management from MIT. He also earned a bachelor's and master's degrees in electrical engineering from, I apologize if I mispronounce this, Pontificia Universidad Católica de Chile. Donnie Hollerschutz is co-founder of the energy and sustainability consultancy INODU with experience in both for-profit and not-for-profit ventures. As an SDM graduate, he holds a master's degree in engineering and management from MIT. He also earned bachelor's and master's degrees in aerospace engineering from the University of Texas at Austin. Jorge and Donnie will present for approximately 45 minutes, and then we will open up the webinar for questions. Please use the chat feature on the webinar to ask questions, and we will respond to as many as possible. Please join me in welcoming Jorge and Donnie for their talk today.
Well, thank you very much, Eric. You made us sound great. We're very excited to hear our introductions. So what we'll be talking today about is, first, we're going to give you an idea of what the trends in wind and solar integration are in Chile. Tell you a little bit about how that has evolved. Then we're going to discuss some of the emerging dynamics of the power system. We'll discuss some of the changes that are taking place in the net load, the regionalization of power system dynamics that are taking place. We'll discuss some of the new modes of operations of existing units, and then some of the emerging socio-technical constraints that are related to these new operational modes, but are also related to other factors. We'll look at how deviations in what was planned the day ahead is affecting the operations of the system. We'll look at some of the challenges associated to the operations of resources. And also, we'll look at the interactions between carbon policy and the power market. Finally, after giving you an idea of the emerging dynamics of the power system, we'll discuss some of the opportunities that are available in the system to utilize existing flexibility that's already present, and also how to encourage new investment and flexibility. So Chile has been a leader in the integration of renewable energy. As you can see in the graph on the left, Chile has integrated more renewable energy, more wind and solar. Here specifically, we're looking at solar, than other South American and Central American countries between 2011 and 2016. Also worldwide, if we look at the percentage of solar and wind that was generated in 2016, Chile is amongst the world leaders. But what is interesting in Chile is that this past year has been incredibly active in terms of wind and solar energy integration. And so what you see in the graph on the left is that solar and wind generation has grown significant to reach levels upwards of 10% or more. And so that really is starting to put Chile amongst the top countries in the world with integration of wind and solar into its system. So what has driven this integration of wind and solar of renewable energy? Well, Chile in 2006 faced the Argentinian gas crisis. So energy prices were quite high for a while. So that created an opportunity, coupled with the lowering of costs of solar and wind technologies. And also what emerged is some opportunities to sign PPAs that drove some of this new renewable energy integration. Right before a regulated auction, a regulated client auction is where distribution companies buy energy for regulated clients in Chile. Right before the 2013 3-2 auction, a block scheme was introduced where the contracts or the PPAs were signed for blocks during the day, the evening, and the night. And after that happened, most of the new projects associated to the winning bids were either solar or wind. What we have also seen is that the prices at which contracts have been signed have been significantly decreasing. It is important to see in this figure that the 2015-1 auction took place in 2016, and the 2017-1 auction took place in 2017. But the contracts for the 2015-1 auction are expected to start between 2021 and 2022. So it's a longer term signal. And also the contracts for the 2017-1 auction are expected to start between 2023 and 2024. Chile is a very long country. It has a very, very long transmission system compared to other countries. It's about more than 3,000 kilometers long. Recently, the Chilean system was divided into two. It was divided into the SINC, the Northern Interconnected System, and the Central Interconnected System. And as of November 2017, both systems got connected. But what is important to note is that what used to be the SINC and the Northern SINC are primarily a thermal system that is being complemented by the incorporation of renewable and an important amount of solar capacity. And the SIC is more of a hydrothermal system. In Chile, in the south, it rains quite a bit, so there's a lot of hydroelectricity, and this is common amongst many Latin American countries like Colombia, Peru, Costa Rica. So one of the important dynamics is how the net load is changing. So what is the net load? The net load is the demand minus the renewable energy, the solar and wind energy generated. So what we show in this figure is an approximation of the net load. The net load is changing, especially the 1 hour ramps that are taking place because of this net load. So if we look at this graph and we look at the 1 hour net load ramps for the 2016 and part of the 2016 and part of the 2017 period, is we see that the most challenging times for the 1 hour change in net load occur during the mornings and during the evening, close to the nighttime. One interesting thing to look at in this figure, which shows all the ramps for 24 hours for every month, is that when the daylight changing, the change in time occurs in Chile, essentially what you get is that the most challenging periods for the 1 hour net load actually change to the weekends. We expect this net load, this hourly net load, to continue to grow and the requirements across the system. So throughout this presentation, we'll be discussing future scenarios. And when we discuss these future scenarios, we'll be relying on simulations we did for 64 different scenarios in the day ahead plan. I wanted to share with you some assumptions we use so you have an idea. We're not going to go into detail about the assumption, but essentially we assumed coal prices of $77.06 and 60 cents in dollars per ton in the SIC, and then $79.60 dollars per ton in the SINC. We also assume gas prices of $6.2 per MBTU for gas. What we also assumed going into these scenarios and considered was that the renewable energy, solar and wind integration, about 2,200 megawatts would be added between now and 2021. And then 5,000 megawatts of solar and wind would be added between 2021 and 2026. All of these values also consider the projects that are already in construction. So if we look at the dynamics of the hourly net load, is we see that the hourly net load could double or triple between 2021 and 2026 based on the scenarios we considered. It is important to note and consider, since Chile is a hydrothermal system, especially in the central part and the southern part, is that the duck curve really doesn't always apply to Chile. And this is something that is also relatively applicable to other places in Latin America that have a large hydroelectric capacity. And so what we show here is the net load curve for a dry scenario in 2021 and a wet scenario in 2021. But what we show as well is we show the net load minus the hydro reservoir generation in the blue. And so what we see in the wet scenarios is that the hydro reservoir generation neutralizes the net load curve, essentially it flattens out the operations of the other manageable generation assets. So we really think that in Chile, the net load minus the hydro curve looks more like a penguin from the Patagonia swimming rather than a duck. And this is common in other places in Latin America as well. One thing that's important to consider as we look at the net load and how it changes over time is if we look at the net load arranged from highest to lowest throughout a year, so if we look at its duration curve, we see that as we integrate more renewables, the net load or the structure of this net load duration curve changes significantly. And what arises is a need for this intermediate capacity that is sandwiched between the peak capacity and the base capacity. And what we've called this is the rise of this middle market, which is this intermediate capacity that is needed to integrate larger amounts of renewable energy. The middle market in Chile hasn't reached about 2,500 megawatts and could double or triple within the next 10 years. One of the things that's important to consider in how this middle market is going to evolve is that before this middle market or this intermediate capacity, units only competed mostly on variable cost. But things like startup cost, startup time, minimum time of operation and shutdown, heat rate of partial load, ramping capacity, frequency regulation capacity, minimum level of operations, and emissions of partial load are going to become more important elements that will determine who ends up supplying the energy of this particular middle market. So in Chile, it's very important since this is a very long country with a constrained transmission system and demand loads in certain locations, specifically in the center and where mining operations reside, it is very important to look at the regional dynamics and the regional dynamics that are emerging. As we see here is that solar capacity has been integrated quite rapidly in what used to be the sink and the northern part of the sink. So here we show in this graph, we show a day, we show February 27, 2016, and then we show how generation evolved 2 years later, essentially. And we see the amount of solar that has been integrated into the system. One thing that's important to note, and we show in this graph, is the red line that you can see. And the red line shows the emissions intensity per megawatt hour generated. And what we see is that as the northern part of the Chilean system integrates more solar, the emissions per unit of energy generator are going to be lower during the day, but not necessarily during the evening. In these scenarios that we considered and I discussed, as renewable energy continues to be integrated in this northern part of the system, what's going to happen over time is this net load curve is going to get chopped into two. So essentially, that's going to influence the operations of the facilities that are the generation facilities in the region, but it's also going to influence how energy is exchanged between the northern part of the system and the central part of the system. Another important element to consider in Chile is that not all wind is the same. Wind is actually quite different depending on the zone where you're located. So as we see in the northern part of the system, in zone 1 and zone 2, which what we have defined in the map, we see that wind really has this interesting curve that coincides with the drop in PV production and also the local peak in demand. But in the south, it is a flatter generation profile. So one important thing to consider is that as we integrate more wind in the north, deviations that occur in the north could increase the stress on the system in the real-time operations right at the time when the sun drops and the net load ramp is taking place. So another element to consider that's important in these emerging dynamics is how existing units are operating. So what we show here is we show data for 2017. And in the y-axis, we show the number of startups for gas units in the system. And in the x-axis, we show the capacity factor for those units. And one thing that we see is what we have highlighted in the upper left corner is that there are units that are operating at a low capacity factor and are starting up significantly already in 2017. And the mode of operation looks something like the graph we show on the right side. What we show on the right side is the mode of operation for one of those units during a particular day. And we show the actual operation in the gray. And we show the day ahead plan for that particular, for the operation of that particular unit in the red line. What is interesting to see is that in 2017, the units in the sink, the combined cycles in the sink, showed these modes of operations and also some open cycles in the in what used to be the central interconnected system. Another interesting thing to show is that there's some units in the central interconnected system that are operating in a more traditional way with a higher capacity factor and less number of startups. But what we see in our scenarios and our projections into the future is that the number of startups for these units in the sink continues to increase drastically over time, reaching 200 to 300 startups per year, which is a significant change in the mode of operations of traditional combined cycle units. If we also look at the operations of coal units for a scenario in 2026, and if we assume, when we assume the carbon tax of $30 per ton, is we see different modes of operation. So let me explain to you the graph on the left. What we have here on the left side in the y-axis is we have the time and minimum level and how much time is spent at that minimum level, minimal operational level. And what we have on the x-axis is the capacity factor. So what we see on the top left corner is that there's some units that are basically, starting up and spending all their time at this minimum operational level. There are some units in the middle that are going to full capacity, but cycling to lower operational level. And then there's some units that are going to their full operational level and oscillating in the cycling mode. Another thing that's important and that's happening and that already happened in the system between October 2016 and September 2017 is that high variable cost flexible units have been used more than planned, what they were planned and estimated they would be used in the day ahead plan. So we see in the sink, here we're showing units in the sink, sorry. We're showing units in the sink. So what we see is these units, these diesel units, these gas turbines are starting up more than they planned, and they're having a higher capacity factor than was planned in the day-ahead plan. Another important element to consider is the new emerging socio-technical constraints. So an important social-technical constraint that we've been observing is, as we see in this particular table, is we see that there's instances between November of 2016 and February of 2017 when units reported that limitations on their temperature, on their effluent temperatures, basically had them define a different mode of operation for their units. And here we see the effects of all the units in the sink. And so what we see is a lot of units in this January period reported these limitations based on their having to meet the limitations on temperature, water discharge. And what happened is that they had to operate under a different mode that they had planned. So they didn't have enough capacity to dissipate heat through their cooling system. Most of these facilities are located by the coast and they have a once-through cooling system. So they didn't have enough capacity to dissipate that heat. So they had to lower their operational levels than they had essentially planned because of these higher water temperatures. What we show here is for the month of for the year of 2018 and the month of February, we show all the water temperatures for the different hours and the different days at Mejillones. And what we see is that water temperatures increase actually coincides with the drop of solar PV generation and spinning reserves. What we see here is we see that, for example, in February 20th, one unit that reported limitations when the temperatures reached the higher levels and they exceeded 21 degrees Celsius, around 21 degrees Celsius, essentially they had to limit its operations because of the lack of cooling capacity. And so there was a deviation from what was planned in the day ahead. Another important element that is limiting the operations of facilities, of thermoelectric facilities, is local emissions limits. And so what we see here in this table is we see the emissions limits for existing units. So for example, for gas units in Chile, there's an emissions limit on NOx, which is 50 milligrams per normalized meter cubed. And this limit must be met during 70% of the hours operating, and the hours operating include startup periods. So what we see in the graph in the left is we see the actual emissions, NOx emissions that were measured for the year 2016 for a particular combined cycle unit. And in the gray, we see the startup hours. In the red, we see the hours reported on the continuous operations. And so what we see is that during startups, there's challenges meeting the current standard, and there's also a challenge meeting the standard of partial load. This also applies to coal units. If coal units were to start up more, they also have a challenge meeting those emission startups during startups. These limitations are starting to affect the operations of the power market. And so what we have here is all the units in the sink in 2017, between April 2017 and September 2017, when they reported the instances that they reported a limitation because of particular matter emissions, NOx emissions, SO2 emissions or other types of limitations. And so if we zoom into one of these limitations specifically, is if we look at a particular coal unit in the sink that reported a limitation on July 11th, 2017, we see how that coal unit operated. They reported challenges with their SO2 mitigations equipment, and the operations changed, and they operated differently than they had planned in the day ahead, and the unit actually had to shut down. Another important element that's taking place is the deviations that are occurring from what has been planned and how those real-time operations are affecting the system. So if we look at a particular day, for example, day on March 13, 2018, in the northern part of the system, we see that the marginal costs that were actual, the real marginal cost exceeded the planned during certain hours, but also in that transition earlier, the marginal costs were lower than expected. Keep in mind that for this scenario, there was a limitation. The systems were already interconnected. As I said, they were interconnected in November 2017, and there was limitations on transmission between both systems. And so we see these deviations in the planned and the actual marginal costs. And so this was a challenging day, because if we look at the SIG North, is we see that the wind and solar generation was much less than expected right before that solar transition. And also the coal generation was rapidly deviating, and it was much less than expected right around 7 p.m. when that solar transition took place. So here in the top graph, we show the solar generation for the sink and the solar generation for the SIG for that day, and we see that transition. What we also see is that during this time, when there's a transition, the system is stressed. Essentially, you have units ramping up to take on that capacity that is being left on the table by renewable, by solar generation. And so what we see here in these two graphs is we show the manageable generation ramp in the sink and the manageable generation ramp in the sink north. So as I mentioned, the marginal cost went up to $148 a megawatt hour, right around 10 p.m. And it went up that high because some diesel units that weren't planned to be operated were turned on to provide flexibility to the system. And the reason, part of the reason this happened is because, well, as we mentioned, the effects of cooling limitations, a coal plant reported a cooling limitation, and it had to lower its generation capacity that had been planned. What also happened is that there was 2 wind farms in the northern part of the system that in the sink that actually during that same time period generated much less than what's expected. And that strained the system, and it created these dynamics. So what we're seeing in the system is, if we look at these graphs that I'm showing, is we're seeing that variations between the planned marginal cost in the day ahead and the real are an important element in determining the operations of the system. So if we see the graph on the left, what I show is the marginal cost, and I show the hours of the year between January 2017 and November 2017. And what I show in the gray dark line is the programmed marginal cost for this particular time period. Then in the gray lighter line, I show the real marginal cost for those particular hours. And what we see is that the programmed marginal cost was underestimated for a significant portion of the year. And there was a lot more variability in the real marginal cost than was programmed. The same is happening, or a similar effect is happening after the systems have been interconnected between, if we look at the data between November 2017 and March 2018. But the thing is, now marginal costs are being overestimated. And essentially, what we're seeing is that during the night hours, this effect is more prevalent. So here I show an example of that particular effect. So if we look at March 26, 2018, in the northern part of the system, you see here in the graphs that the marginal costs were overestimated during the nighttime, or during that transition into the night. And essentially what happened is that the imports from the SIC provided flexibility and lower the marginal cost between 7 p.m. and midnight. So what we see also in the graph in the bottom is we see the flows between the SINC and the SIC. But I showed you two examples where there was an economic impact or an economic deviation in the system. But that's not always the case. That only happens sometimes. As we see here in another example, is that in September 23rd, 2017, in the SIC, before both systems were interconnected, there was a deviation. There was much less renewable energy that was expected, that was generated in the system, essentially, wind and solar. And so what happened? Well, during that time, there was a good amount of hydro reservoir capacity. So that hydro reservoir capacity was used. And also gas provided some flexibility. Gas generation provided some flexibility. It generated more than it expected. And, nothing really happened to marginal costs. They were exactly pretty much as they were planned. So now I'm going to transition it over to Jorge Moreno.
Okay. So thanks, Donny. So now we're going to provide some insights regarding how the operating reserve services are planned in the system and its link to the energy generation service. As a general overview, in this slide, we present the planned reserve for frequency regulation in the system. What I'm showing is, in the graphs, is the primary frequency regulation for contingency, the primary frequency regulation for up regulation, and the secondary frequency for up regulation as well, for the SINC and the SIC. In the SINC, the thermal, coal, and gas units and the grid-scale battery system provide operating reserve services. In the SIC, reservoir hydro and thermal units provide the operating reserve services. In dry scenarios, gas units also have a role providing reserves in the SIC. Recently, the interconnection between the SIC and the SINC allowed the reduction of reserve requirements for primary frequency control in the system. Now, if we focus only in the SINC and the SIC North, this slide shows how primary frequency regulation services are being planned in the system. First, primary frequency regulation for contingency, where grid-scale battery storage systems can account for a large portion of that market. Second, for primary frequency regulation, up and down, where coal, gas, and even diesel units are being planned. If we look at how secondary reserves are being planned, we can see that this market is linked with the availability of solar resources during the day, which is not necessarily the time where those amount of reserve might be needed. However, this behavior is coupled with the reserve requirements after sun hours. When there is renewable curtailment and transmission constraints, price signal drops to zero. Look how reserve supply tightens up after some hours. As we have seen, the effects of deviation can be challenging during these hours. It is important to note that currently renewables are not providing secondary frequency control for down regulation. Here, there's an opportunity for renewables to provide that type of services. Before the system was interconnected, we observed that where the reserve tightens up after some hours, overall, more gas and diesel had to be used than expected in the day ahead plan. The graph shows the cumulative deviation from October 2016 and to September 2017 for gas and diesel units. When you look at the 20-minute variability associated to the generation level of wind, as shown in these graphs, the maximum expected variability is when wind as a whole is at intermediate generation level. Therefore, as wind penetration increases, the reserve requirement shall be adjusted to cover this variability. For some of the scenarios that Danny discussed, these graphs shows the effects in the system operating cost, CO2 emissions, and curtailment of renewables. If no flexible generation projects are added, increasing spinning reserve requirement increases renewable curtailment, CO2 emissions, and operating costs for medium hydrological conditions. You have to find the right balance between spinning reserve and non-spinning reserve services. So now we're going to talk about the interaction between carbon policy and the power market. So the next slide. Okay. So for 2017 and the projected scenarios, the graph shows the generation mix to satisfy the net load. If we account for a carbon policy, carbon tax has a critical implications in how the middle market is served. The optimal way to serve the middle market creates opportunities for new assets. If no carbon policy is in place, there are scenarios where coal generation increases as the demand increases, without adding new coal power plants in the system. Now, though an increase in the price of CO2 reduces total emissions in the national electricity systems across all scenarios, it does not affect coal and gas units operations in the SIC and the SING in the same way. In the SIC, an increase in the price of CO2 leads to a significant reduction in the generation by coal units and an increase in generation by gas units in all scenarios. In contrast, as higher the price of CO2 reduces coal generation and increases gas generation in the sink only to some extent. Thus, the replacement of coal generation by gas units requires that alternative providers of efficient flexibility and reserves appears in the sink. This flexibility and reserves could be provided by the installation of affordable storage or generation units with very low minimum stable levels and rapid ramping capabilities, which will subsequently enable CO2 price signal to have its intended emission reduction effect in the sink. So finally, what are the opportunities to utilize existing flexibility and encourage investment in new flexibility? As we have seen in the presentation, The development of the middle market is key for the effective and efficient integration of renewables. It is important to note that the capacity needs are changing with the emerging flexibility needs. And today, flexibility is not being fully remunerated. It's important to ask two key questions. How will Chile keep integrating more renewables efficiently? And over time, how will Chile efficiently replace its existing thermoelectric assets with newer, more flexible assets? In this table, we present an estimation of generic lower bound variable operation and maintenance cost of a 280 megawatt subcritical core units and a 400 megawatt combined cycle unit, considering different cycling operational modes for each unit. The most significant effects in the V&M cost for both core units and a combined cycle gas turbine are caused by the increased number of plant startups. The exact V&M cost will depend on many factors that can be site and plant specific, including operational modes, plant configuration, maintenance and operation procedures, among others. The presented estimation is only indicative and illustrates the general trend of increased V&M cost of thermal units through a greater cycling, specifically increasing the number of startups of CCT of combined cycle units to 300 times. The policy levers to incentivize investment into new flexibility options for the systems are intertwined. Emission limits during startups and emission limits at partial load should be carefully defined, particularly for gas power plants, because they have important implications in the flexibility of gas units, which has greater operational flexibility compared to coal. Focusing on just improving the parts of the policy independently will not guarantee improving the performance of the system as a whole. The performance of the electricity system will depend on how the policy levers fit together, not what they achieve separately. Should be improved to reward greater flexibility and updated to reflect the operational constraints as well as new modes of operational conventional power plants. Different mechanisms for pricing of reserves can help the wholesale market function better and strengthen the link between the energy and the operating reserve services. The improvement of the performance of the electricity system will not be driven pondering about the future, but rather really understanding what is happening today to find opportunities to improve the system for the long term. Key areas to observe to find opportunities for flexibility are listed in the table. Performance of existing thermoelectric facility, variability and deviation from the planned scenarios, deviations between the actual and expected economic performance in the system, new constraints which emerge as the system operates, the behavior of the middle markets and its interaction with environmental restrictions and CO2 policy, interactions between energy and operating reserve services, and finally, performance parameters which will be more relevant to address new challenges, such as satisfying the net load or improving regional needs. So we have been doing a lot of work in understanding the challenges of integration of renewable from different disciplines and perspectives. Here are some conferences where we will present our work during the next 4 months. So thanks. So now we can open the conversation for questions.
Thank you, Jorge and Donna. That was a very well put together presentation. So we don't have any questions just yet. So just a reminder for our people watching, please use the chat function on the right-hand side there if you have any questions for Jorge or Donnie about the presentation today.
So we'll go back to
Yeah, if you guys would like to go back to anything, please feel free
to. So we'll go back to a little bit of some of the work that we have done.
You might want to pull your microphone a little bit closer, by the way.
Yeah, so the work that we
And actually, we do have a question from Thomas Grandry. Why did you set 30 USD/T CO2 emissions?
Right. Well, that's a really good question. So one thing that we looked at is we looked at
Carbon disclosure project, transmission corridors.
So we looked at the carbon disclosure project emissions corridors, essentially. And based on that, the carbon disclosure project is basically a survey that's been done amongst different investment professionals, industry professionals, to gauge their expectations of what the future price of CO2 could be in the future. And based on, and they developed some corridors of where most people that were surveyed lie within an expectation of a carbon price going into different future dates, essentially. And so we looked at that. We also looked at some of the work that's being done here in Chile and the discussions around CO2 policy. We also looked at, there's a definition for a social CO2 price as well that's defined by the Ministry of, I think it's a Ministry of Economy or, a ministry here in Chile. I forgot exactly which ministry, and we looked at the price that they set. So essentially, we determined different scenarios, and we modeled different scenarios, but we considered a CO2 price in 2026 that could either be $30 or $45.
Yeah, we ran simulation from $5 to $45.
Exactly.
And in this presentation, we only show the case for $30.
Exactly. Yes.
All right, we have another one here from Thomas. Great presentation, thank you. What are your thoughts on grid decentralization on a household, municipality, county basis? And further, based on your analysis, what level of need for newly installed fossil generation power sources do you foresee, if any?
Okay, so I'll divide up the question into two. So I think in Chile, there's a great renewable energy resource. Going to the first question, asking about distributed energy resources, and essentially there's a lot of great solar resource. So I think there's an opportunity for distributed solar resources, and the demand both at the residential and the industrial level to contribute with generation capacity, essentially. And I think that's an opportunity that's emerging, and I think that's something that's changing, and it's going to continue to change into the future. In terms of new thermoelectric capacity, we do see that there is a significant amount of thermoelectric capacity in the system installed already in terms of coal and combined cycle units. Essentially, what we do see is that there's opportunities for more flexible thermoelectric capacity, essentially units that could, be more environmentally friendly and also have new performance parameters that are becoming important to what we see being the observed operations of the market currently and in the future. And that means, having lower startup costs, having more rapid ramping capacity, those sorts of things, being able to provide, frequency regulation without having to be at a minimal technical level or a very low minimal technical level.
Yeah. So, yeah, we can also see in new assets that can provide non-spinning frequency regulation services.
All right, we have one from Micah here. Thanks for the great work and presentation. Have you evaluated the impact of fossil fuel plants' anticipated retirement that has been announced by the generation industry?
We didn't specifically retire any plants. So essentially, what we did in these scenarios is we looked at CO2 prices or a CO2 tax essentially being incorporated into the determination of the variable cost of the unit, and essentially including that and seeing how units would behave based on that CO2 tax price, essentially, or that CO2 tax cost. And we observed the results based on that, which is, it's a different approach. It's putting essentially a price on carbon and seeing how it behaves. So it does restrict the operations of units with higher emissions intensity in the future. One thing that we see, and we showed in a slide, is that essentially the CO2 price has a very important effect on the middle market and how gas and coal compete for that particular middle market. And it can also have an effect on the new investments that come about into that middle market.
And then the dynamics are very different if you look at the SiC and the zinc.
Exactly.
Everyone here from Joan. Excellent presentation, thank you. It sounds like Chile would be a great market for energy storage. What are your thoughts there on the challenges and opportunities there?
I think as we mentioned, one thing that we do see an opportunity for more flexibility into the future coming from storage and other types of units. But what Jorge mentioned, and I think it's an important consideration, is that in order to incentivize this flexibility, you need to, you really need to think about different policy levers that are intertwined. And currently, the way those policy levers are defined do not essentially provide enough incentives for some of these technologies. So moving into the future, I think adjusting these policy levers will be key in determining how these new flexible technologies get integrated. And when we showed the policy levers, it's really thinking about the ancillary services market, thinking about the capacity market, thinking about CO2 policy, transmission planning. Those things, how you define those things, will really determine the opportunities in the future. But what we try to show in our presentation is that there are challenges that are emerging in the operations of the system. And so essentially, what's important to keep in mind, as we mentioned in our presentation, is that there's opportunities to solve some of those challenges now, whether they be solved and met with batteries. That's, it's gonna be determined on how those batteries are remunerated or how they're paid for by these different mechanisms. Another thing to consider that's important is, Chile has installed a significant amount of battery capacity, grid scale battery capacity, and was one of the first countries to do so. And it did that under a different context where, you know, prices of energy were really high and under a completely different context than today. But essentially, those batteries that are in the system are providing, as we showed, you know, that primary frequency control, the contingency part of it.
Yeah. So batteries can provide different kind of services, right? So you need to think also about what type of services will you provide with the assets. Okay. So will you provide? Will you install batteries for frequency regulation? Will you install battery for time shifting or energy trading? For both kind of services or for other kind of services? So you really need to think about this kind of different services that you can provide, and also looking at the regional dynamics where the assets provide or generate more value. So the dynamics in the north are different from dynamics in the south. So different if you install a battery behind the meter, in front of the meter, so different. Yeah. There are different options.
Yeah, I mean, what we're seeing is there's an opportunity for niche installations of different types of technologies that provide this flexibility, and it really depends on the location, the particular dynamics in the region. But in order to find those opportunities, it's important to, you know, understand some of the dynamics that are taking place, and also as some of these you know, new or opportunities to change the existing policy levers, then that'll grow the market and create more opportunities for these flexible technologies.
All right, well, I believe that's going to wrap up the questions that we've had so far. So Jorge and Donna, thank you so much for your wonderful presentation. And a reminder to our viewers that the slides as well as a recording of this presentation will be available on the SDM website later this week. So thank you, Jorge and Donna, again. And we'll hopefully see everybody pretty soon.
Yeah.
Thanks. Appreciate it, Eric.
Bye.